So the second subdivision is proving that the equivalence relation of congruence modulo n has n distinct equivalence classes. So let the equivalence class of some integer a, any integer a, be denoted by this symbol. We call this the congruence class of A modulo n. Okay, and some authors denote this same thing by this symbol A bar, but we are not going to use this. Now, because A is any integer, so by the Euclidean algorithm, there exist integers q and r such that a is equal to qn plus r, where r satisfies these inequalities, right? Then you can see that n divides a minus r, because a minus r is qn and q is an integer, so n divides a minus r. That is, a is congruent to r mod n. So a and r belong to the same congruence class or same equivalence class under this relation congruence modulo n. Hence, the equivalence class containing A and that containing R are the same. Okay, now looking at this range of variation of R, we can see that there can be at most n congruence classes. Hence, we have already written this, right? So, the only equivalence classes we will continue to say equivalence classes at least in this proof, okay, because the statement of the lemma says that it does not mention congruence classes, it mentions only equivalence classes. Congruence class is something which we have defined here. So we will later on say congruence class modulo n, but for now we will say equivalence class. The only equivalence classes are these, depending on the possible values of r. Now, as of now, we don't know whether these are distinct. In fact, we can see that there are n symbols here, starting from 0 to n minus 1. But they may not be distinct, because you see, we have already said something along these lines. For example, if we are considering the modulus 10, then we have 12 is congruent to 2 mod 10, So the congruence classes 12 and 2 are actually the same thing, same set. So it may be the case that some of them are equal. Now we will prove that that is not the case. Actually these n congruence classes are distinct. So thereby we will get exactly n congruence classes. Whatever we have done so far allow us to say that there are at most n congruence classes, because whatever integer we choose, the congruence class containing that integer will be one among these. We will now show that they are distinct. Okay. Next, assume I is equal to class containing j for some integers I and j satisfying these inequalities. Now we look at this, you see, what we are assuming here is that each of I and j is one among these numbers from 0 to n minus 1. Now given arbitrary such I and j, one of them is definitely greater than or equal to the other. So without loss of generality, we have assumed j to be at least as big as I, and both of them are less than n and both of them are greater than or equal to 0. So what does this tell me? Then I is congruent to j mod n, or n divides j minus I. Okay, so that's the meaning of this congruence. Now n divides j minus I, since j minus I is a non-negative integer less than n, we must have j minus I equal to 0, or j is equal to I. So what we are saying here is this. You see, n divides j minus I, that means j minus I is an integer multiple of n. Now at the same time j minus I is non-negative. Why? Because j is greater than or equal to I. Now the non-negative integral multiples of n are this: 0, n, 2n, 3n, etc. Now j minus I lies here. It is strictly less than n, and it is greater than or equal to 0. Why is it less than n? It's because j minus I is less than or equal to j. Why? That's because I is non-negative. The maximum value of j minus I is j when I is 0. Otherwise, it's strictly less than j. And in any case, j is less than n. So j minus I is always strictly less than n. So the only possibility for j minus I to be a multiple of n is for it to become equal to 0. That's why we have this. So j is equal to I. So this proves that these equivalence classes are distinct. Hence, the equivalence classes (0, 1) all the way up to n minus 1 are distinct, and so there are n distinct equivalence classes. Okay, so this completes the proof of the second subdivision. Now we move on to the third one. Let me just refill this. I think I am running out of ink. Okay, give me a moment. The third one asks us to show two things, right? How congruence behaves with respect to addition and multiplication. So we have A is congruent to B mod n and C congruent to D mod n. Then n divides A minus B and n divides C minus D. Okay, let me just see one thing. N divides A, yes, that's how we have defined this. It does not matter. See, once we have proved, so what I was worried about is whether I should write A minus B or B minus A. But that does not matter. Once we have proved that this relation is symmetric, when A is congruent to B mod n, then B is also congruent to A mod n. So whether you write A minus B or B minus A, it does not matter. Okay. From these relations means these two relations we have. So if n divides these two integers, then n also divides their sum, A minus B plus C minus D, which is nothing but A plus C minus B plus D. That is A plus C is congruent to B plus D mod n. Okay. So this is the first congruence we have to prove. Also, okay, the next one is AC is congruent to BD mod n. So for that, you look at this. Since n divides A minus C, so n divides C times, n divides A minus B, so n divides C times A minus B, plus n divides C minus D, so n divides B times C minus D. And if I simplify this, I get AC minus BC plus BC, they cancel out, minus BD. That is, since n is dividing AC minus BD, so AC is congruent to BD mod n. So this was the third subdivision. Now the fourth one, the last one. The fourth one says it gives us these two things. AC is congruent to BC mod n, and also the condition that C and N are relatively prime from the above congruence we have N divides AC minus BC, or which is the same thing as A minus B times C. Since C and N are relatively prime, this implies N divides A minus B. What are we using here? I mean, how are we concluding this? We are concluding this by using one of the previous, I think, a corollary to a lemma. If you go back, you can see what I am talking about. The specific result is this: if a number A, okay, don't mix up A, B, C with these things. Let me use some other symbol. If a number, say x, divides, number means integer, a product of two numbers y and z, and x happens to be relatively prime to y, then this implies x divides z. This is the result we have used here. Hence, expressing this in terms of congruence, we have this. So it's a cancellation law. It's somewhat like this one. If AC, A and A, B and C are real numbers, then AC is equal to BC, and it's given that C is non-zero, then A is equal to B. And this condition that C and N are relatively prime should not be taken lightly, because if it's not the case, then the cancellation law may fail. For example, you can look at this: 2 times 3 is congruent to 4 times 3 mod 6. Why? Because this is 6 and this is 12. So 6 divides 2 times 3 minus 4 times 3. And this is nothing but 6 minus 12, which is minus 6. This is true. However, 2 is not congruent to 4 mod 6, because 6 does not divide 2 minus 4. So we cannot cancel 3 from both sides of this congruence. And the reason is that 3 and 6 are not relatively prime. The greatest common divisor is 3, not 1. Okay, so this condition should not be taken lightly. It's somewhat like the one we have for an ordinary equation where C is non-zero. Okay, now this lemma, I believe it's lemma, right? It's been quite some days since I started this thing. Yeah, it is lemma. I was busy with some other things, so I was not able to film this or make these videos. Anyway, so now this lemma allows us to do something which is actually the essence of abstract algebra or modern algebra. That is, take some objects and define some operations on those objects and see how that system behaves. Okay, now in that direction we can define operations on a set, but let me first define that set. let Jn be the set of all congruence classes modulo n. That is, Jn is this set. N is already a fixed positive integer. Okay. In the context of this discussion, n is given to us. N is the modulus of our relation congruence modulo n. Now this notation Jn, Herstein uses Jn. More commonly, authors use this notation, Zn or Cn. This will be seen more commonly in many mathematical texts. However, they are the same thing. Jn is called the set of integers modulo n. This name may create some confusion. See, when we say Jn is called the set of, it's a set, one can see that. The set of integers modulo n, this does not mean, this is one mistake that people often make. It's not a set of integers, it's a set of sets. Set of congruence classes modulo n. Usually they are also called integers modulo n. Okay. Why? Because when we think of 0 in this context, we are really thinking of the set of those numbers which leave the remainder 0 upon division by n. Those integers which leave the remainder 0 upon division by n. So in that sense, those numbers are thought of as congruent or equivalent. That's why this is an equivalence relation, right? So in that sense, we say integers, but we add this separately modulo n with respect to the relation congruence modulo n or up to division by n. Okay. Anyway, so on this Jn we can now define two operations. For two congruence classes, we define addition. The definitions are very easy to understand, but there is a problem with these definitions. I mean, an issue which needs to be addressed. And similarly, we can define multiplication. So addition is just it is by definition the congruence class containing the integer a plus b. Like that, the multiplication gives us the congruence class containing the integer ab. Now what is the problem with this definition? We have to show it's not really a problem, but rather something that comes to our mind when we think about this definition somewhat more deeply. This can be shown by a simple example. Think of the modulus 10, say n is equal to 10. So now we are in J10. In J10, we have these congruence classes. Okay, and one can easily see that these classes are equal. Because the congruence class containing 12 is equal to the congruence class containing 2. That's because 12 is congruent to 2 modulo 10. Same is the case with 4 and 14. 14 is congruent to 4 modulo 10. Now if I use this definition, on one hand I have 2 plus 4. By definition this is nothing but this congruence class. However, at the same time, it's also equal to 12 plus, I can take say 14. I can keep 4 here also, but let's just see the wild case. So this is 26. Now it better be the case that these two are equal. In fact, they are equal, and that follows from this congruence. 26 is congruent to 6, not 10. Because 10 divides 26 minus 6, which is 20. But we have to prove this, because otherwise, using different representatives for the same congruence class, we will end up having different answers. If that happens, then our operation is not well defined. So we have to show that this operation, this as well as this, the addition and multiplication are well defined. Okay, now this we will do in one exercise problem. Now, for now we are assuming, let's just assume that the operations are well defined. That is, whatever integer I choose to represent the congruence class, since in the congruence class I have many integers, I can pick any one of them and write it here, if that belongs to the same congruence class. Whatever I choose that to be, my end result, the congruence class that I have on the right hand side, that turns out to be the same. Okay, that I am assuming for now, which we will show in one exercise. Now let's look at some of the properties that these two operations have. And they are what we already expect them to have. That is the usual commutative associative laws. So let's just list them. These two operations on Jn have the following properties. The first one is, of course, the commutative laws. The order in which these operations are carried out, that does not matter. Then we have the associative laws. Okay, and then the distributive law. Actually, there are two distributive laws, but whenever multiplication turns out to be commutative, I mean, see, this is the thing. we are going to study some systems in which we will come across objects, or operations which behave like ordinary addition and multiplication. That's the idea of a ring. So whenever multiplication is commutative, addition will always turn out to be commutative. We are going to consider those types of operations which behave like addition, not just in the sense that the other laws of addition are true, but commutativity is also true. But that's not going to be the thing always with the multiplicative operation. In this case, it's the we have a commutative law for multiplication, but in general, we will see that the operations we consider as multiplication, they are not always commutative. Whenever commutativity is available, then there is only one distributive law. Otherwise, there are two distributive laws. These things will become more clear when we start ring theory proper. So for now, let me just write this. This law, as you already know, it links the two operations, addition and multiplication. And you can see that the laws have the same structure that we already know, as if these are not congruence classes and these operations are not some newly defined operation, but they are just integers and these are ordinary addition and multiplication. In that sense, if you think, these are just laws that we already know. Distributive law. Fourth one, identity. Fourth one, fifth one, sixth one. There were more, right? Have I missed something? Oh no. They have numbered these because there were 7, I remember. Numbered these things separately. That's why they got so many. This is the 5th one. This is the 6th one. And this is the 7th one. Usual stuff that we already know about the integers and ordinary addition and multiplication of them. Now these laws will be we will be asked to prove these laws in one of the exercise problems. Okay. Now here the text part of this section ends. This Jn, which is the set of integers modulo n, this plays a very significant role in ring theory. In general abstract algebra and number theory. We will come across this again and again when we study those systems. Okay, now let us move on to the exercise problems, which are by far the most important part in Herstein's book. The first two exercise problems, I think we have already solved them while discussing these things. So let us now start with the third one again. So this is exercise 3. So what this says, the least common multiple of integers a and b is defined to be a positive integer d such that the following two conditions are true. So this definition is somewhat like the one for greatest common divisor. So common multiple, right? So a divides d and b divides d. That is a and b should both divide d. D must be a common multiple of a and b. And if a divides c and b divides c, where c is some integer, then d divides c. If these two conditions are true, then d is said to be the least common multiple of a and b. Now the exercise asks this: prove that, I have not said how we denote it. We denote the least common multiple of a and b by this symbol.